Okay. So this lecture, finally, after all the weeks of preparation, is actually bringing us to sort of the research frontier. I mean, even the last lecture was pointing at how we should use these block entropy curves and look at the shape of them. This week and next week, we're going to delve into this in much more detail and talk about things that very much go outside of conventional information theory and communication theory. Much more directed to the questions of what different kinds of information are there. And so, in some sense, the sort of rate of ideas will be, new ideas will be quite high. I hope that the way it's presented will be relatively clear in a geometric sense. I'll introduce some of these ideas and different measures of information using these block entropy curves. So there'll be kind of a unified graphical way of thinking about this. This week, we're very much just sticking to this paper that's on the reading list, Regularities Unseen, Randomness Observed, this review from about 10 years ago. Sticking pretty close to it. So, previously, we've been really talking about information in Shannon's setting in terms of measures of surprise, measures of randomness, unpredictability, and we sort of adapted those or his concepts of information and uncertainty to the block entropy in word distributions for words of length L. And last time, really the only question we were sort of asking about is for very large word lengths, what this rate of increase was per symbol. So we wrote down a version of this, which is just the two-point approximation, two-point slope approximation of this. The Shannon entropy in words of length L minus the Shannon entropy of words of L minus 1. And then we showed that we gave this an interpretation. This is the true source entropy rate as defined in Cover and Thomas, except now we have definitions that let us do this, talk about this for any complex process. Again, in Cover and Thomas, just to make it tractable, they just focus on IID processes where you can write down essentially an order 1 Markov chain and calculate things directly from that using that formula. State averaged branching uncertainty. Now that we have this quantity, that entropy rate for arbitrarily long words, the growth rate, now there's some other issues, how we calculate it. In particular, if I had a process and not a model of it, how would I estimate this? You could, of course, empirically estimate your word probabilities and then plug those distributions into the Shannon P log P formula and get, again, this series of scalar numbers as a function of L, and then try to approximate the slope. One of the problems with that, of course, is that if the source is even a little bit random, imagine the fair coin, the number of words whose probability you have to estimate grows exponentially with the length. So you're kind of screwed if you want to do this. Or the other way to think about it is that that's why we build models, to sort of deal with the sort of infinite case in a sense. So we'll talk about that more directly in the spring. But anyway, so basically so far the main notion of information we've been using is surprise. It could be the surprise when I pick out a word of length L from the L word distribution, or it can be the asymptotic incremental surprise when I add more symbols and make longer and longer words and look at the rate of growth of the block entropy, which is the entropy rate. So, in some ways, that's sort of all mostly set up. What I want to focus on today and to some extent on Thursday is how we can use the same block entropy curve to define measures of memory and information storage. And this is not something that's in Cover and Thomas. This is relatively new, and in some sense, this will take us to yet another classification scheme, which, again, seems to be my habit, is to keep coming up with ways of figuring out how rich nature can be. One way of doing that is coming up with these classification schemes. They're different classes, and with an enriched set of measures of surprise, but also memory and information storage and processing, we now can kind of delineate a much richer class of processes out there. So just to actually give the punchline for this week, these measures of memory and information storage are really complementary to these measures of randomness. In other words, if I give you a process Shannon would say, oh, think of it as an information source and calculate the entropy rate, number of bits per symbol, the irreducible randomness or unpredictability of the process. And we're saying, no, there are actually some other very important system properties that you'd also want to know. And I'm going to argue as important and complementary to this notion of surprise and unpredictability. And then this will be setting us up for spring to start talking about, well, okay, you say there's memory. Exactly how is that memory structured inside the source? So we come back in the spring and we have to revisit our very notion of what it means for a system or process to be in a state. What are these hidden states? We've been using models that have hidden states, but that's us making a model. So we need both of these things, both measures of randomness and of structure. So I want to sort of give a quick summary of what we did last lecture with the block entropy curves to set up and motivate the measures of memory. So we have our block entropy growth function, h of L. And what we talked about in detail was if L is large enough, then there's this sort of what seems to be a linear increase. In other words, the ansatz here, the assumption or kind of working hypothesis is that at least for long enough L, there's this linear growth rate for the block entropy, and that's this entropy rate quantity. So the units here are bits. The units here are length, and then this is or symbols, and then this is bits per symbol, the irreducible randomness. So the units all work out, right? And then this h mu quantity, we could approximate that as either the difference between the block entropy at words of different length, or if you remember, it's a simple rewrite to give that as a conditional uncertainty. What's the uncertainty in the next symbol given some infinite past? Okay. So here are some examples, which again, you can go calculate in that interactive lab. You can go play around with it, change some parameters and whatnot. So we talked through before what the block entropy looks like for the fair coin. It's just this linear increase with a slope of 1. If we have a bias coin, then here in the dashed line, again, a straight line, linear increase, but at a lower slope, in other words, a lower entropy rate, because it's biased, maybe more heads than tails. So this is a numerical example that you can calculate. Sort of not very interesting. Again, sort of argued or pointed out that this is what block entropy curves look like for all IID sources. Okay. But we have other things we've been studying, like here's the block entropy plot for the golden mean process, right? No consecutive zeros. So there's actually some kind of regularity. Something inside the process has to remember, oh, I just saw a 0, I have to produce a 1. So there's some sort of mechanism inside. But that also causes a restriction. If you remember the mosaic of word distributions, there's this, as we go to longer and longer words, there's actually this fractal set that's all the words that contain 0, 0, which is forbidden. So this kind of cleaves out this self-similar set in the space of possible words. We can summarize that rather than looking at all the detailed probabilities for longer and longer words with just looking at h of L. And what we see here is it's not a straight line. Well, at least it starts out at some slope, and then there's this kink here at L equal 1. And then it does finally very quickly, reach this linear growth. So that's L equal 1. Well, we know that there is an order 1 Markov presentation of the golden mean process. Right? State 1 can go to itself or to 0, but if you see 0, you must come back to state 1. So order 1, notice L equal 1, and we finally reach this linear asymptote where, for longer words, if we just look at the rate of increase, it's going to be exactly at the entropy rate. So in some sense, for this process, because of the way it's structured, we only have to go to words of length 1 to sort of see the asymptotic linear increase, long word increase. It's already reached its asymptopia at L equal 1. And that's dual to the fact that there's a very simple restriction. This kind of hint that there's some internal structure in the process. So this is our first kind of suggestion that just looking at the shape of the block entropy curve can tell us something about, in this case, the Markov order. Yeah?
For clarification, you're saying it reaches its asymptotic property or whatever at L equal 1?
Yeah.
At L equal 2, because you don't really know the slope of that. L equal 2, would it make sense that you would need 2 letters to know that you can have 2 consecutive zeros?
Yes, yeah, and we'll have to deal with, it's a slight definitional thing. I can write down the order 1 Markov chain and calculate from that. So that's what this is indicating. But you're right, if I wanted to actually calculate that slope and the correct entropy rate, I'd have to look at the difference between words of length 2 and words of length 1. You're right. So and the way the definition goes, this is an order 1 process. Where the H of L curve finally meets this linear asymptote.
Question?
Yeah.
So it seems like in this case that it would never actually meet the asymptote. It's always shifted up a little bit, unless I'm misinterpreting the definition of the H.
Well, it comes from below to whatever it's going to do. I'll give you some examples that'll kind of clarify this a little bit, but it's actually converging from below to this asymptote. It's monotone increasing, and it's converging to some kind of linear asymptote. And actually the question, the main sort of point today is trying to figure out what this linear asymptote is. But here's some other examples. Just right now, what we're doing is talking about, oh, okay, at least we're a little bit comfortable with this long word rate of growth, somehow the intrinsic unpredictability, intrinsic randomness per symbol, the entropy rate. The question is, well, how do we get there? And it's how we get there that are going to be signatures for how structured a process is. So, but let's move on. Period 16 process. There's some word, binary word of length 16. I set it up so I had no subwords in it that were periodic. And notice, so I'm plotting H of L, and it grows and grows and grows. Actually, the 2-point slope keeps changing until out here, it happens to be at length 12, interesting puzzle, not length 16, it finally flattens out. It's a periodic process, so at least eventually, if we take enough of the history into account, we'll see what the period is, and then from that point forward, by definition, it's periodic. There's no uncertainty in the next symbol. Entropy rate is 0, slope is 0. Now, there is this interesting way of getting up to here, and we'll talk about that on Thursday. In fact, there could be different length 16 templates for the binary word that I was repeating to calculate this, and they would actually approach this. But anyway, at least for sufficiently large L, on the order of the period, certainly longer than the period, the block entropy curve flattens out and has 0 slope. Yeah?
Are there curves like logarithm or square root of x that
Absolutely.
don't ever have an
Yes.
asymptote?
Yes. Yes. We'll get to some examples. Those are the fun processes. So here's one, and I'll come back to analyze this, but now I just want you to start thinking graphically in terms of these block growth curves. So this is something called the random XOR process, and we'll come back to it later on. But what that is you flip one coin, you flip another coin, and then the third symbol you output is the exclusive OR of the previous two. Flip 2 coins, XOR, and so on. Okay, that's some binary process. Generate a long string and then calculate this H of L. Well, this thing just kind of keeps, not even very, is it reached its asymptote? Where is it? It's kind of hard to figure out what's going on here. It just slowly curves over. I mean, if you could actually look here, it still is curving over up here. Turns out this thing, the random XOR process, has something like 5 internal states. But I just gave you the process definition, so how would we come to figure that out? So that's an answer for the spring. Anyway, I don't know what's going on here. So there's this question. First question, how long a word length do we have to go so that we can actually sort of pick up the intrinsic randomness of the process? The picture is very clear with the golden mean. Finally reach that linear scaling after L equal 1. Random XOR looks like it's sort of a qualitative call. Is there some principal way of doing this? Are there processes for which you have to go to infinite L? The slope keeps changing, like say a logarithmic dependence or something like that. And what does that mean? Anyway, if you have a process that has that, this kind of a very empirical view we have with the block entropy curve shape, what's going on? So this is really, so this question really boils down to thinking about how these estimates of the entropy rate reach the asymptotic infinite length value. So one way to probe that is to look at, instead of entropy growth, what I call entropy convergence. It's really to look at this length L approximate, this 2-point slope approximate of the curve, and just plot that as a function of L. And actually, from here on forward, I'm going to introduce an operator that's like a discrete symbol derivative, delta here. And it's just merely, it's d big L. So when I apply that to h of L, what I mean is this 2-point slope approximation of something. And so here graphically, what we're doing is it's just plotting the slopes now. We had those from the block entropy curves. In some ways, this at first blush is just a different way of presenting the data, but it makes it a little bit clearer about the convergence process, how long it takes, how large a word we need until we get to the entropy rate. Okay, so here's the entropy rate in this kind of cartoon picture, the dashed line, and then somehow this h mu of L, this 2-point approximate of the entropy rate, converges to that. In fact, you can show, well, we talked about it last time, that this 2-point slope is actually monotone decreasing. That could be flat parts, but it's monotone decreasing. So it converges from above to the actual entropy rate. Okay. So the way to think about this, the sort of mnemonic for this picture, entropy convergence picture, is that you sort of imagine that you are looking at it, you don't know what this asymptotic L is, but you're looking at finite L. And if you look at the process with too short a word length, your approximate, your estimate, 2-point slope estimate of the entropy rate, how random the process is above the true randomness. Right? So in other words, if I take too crude a statistic, the process will appear more random than it really is. And the goal, of course, is to sort of take more data, look at more sophisticated statistics over longer words until we get better and better approximates of the true unpredictability or randomness in the source.
This is related to, in some sense, going to a point where the process becomes ergodic and some time scale, or?
Well, so these are all ergodic. We're assuming ergodic processes. We might, actually, if there's an interest, you can extend these ideas to non-ergodic processes. It takes a little more, takes this notion of state we need to rebuild in the spring. But yeah, so these are stationary ergodic processes, sort of well-behaved statistically. We have, in a sense, a single kind of statistical component, and its parameters aren't changing over time. And, right. Now, there might be some hints. I mean, you could, maybe later on it'll start to make sense. Imagine this takes a very long time to converge. Could that be some indication of non-ergodicity or highly structured processes? So let's get through the examples here. Okay, so that's the main idea. So in this entropy convergence curve, the idea is we converge from above, and what that means is that the process appears more random, the green line is above the dashed line, than it actually is. So we can then, this entropy rate, h mu of L, this approximate, is it's actually like an information gain. You can write it down in terms of Kobuck-Leibler gain. And it's sort of the distance between, statistical distance, again, that quotes around the use of the word distance, between the distribution over length L words and words one symbol shorter. Right? If I go from length 7 words to length 8 words, my estimate of how random the process is drops. Therefore, my ability to predict improves. And we sort of encountered something like this notion of redundancy. If you remember back to, say, the modem example, right? There's this sort of way of looking at a process in terms of just log of the alphabet size. If I have a binary alphabet, if I make measurements, I have to store those somewhere. So I'm paying for that storage, 1 bit. You go out and you buy your DRAM chips, you pay for all 32 gigabytes, but you rarely use them, but there they are, you have to pay for them. So here, there's this sort of a distance between what you're having to store and what the actual randomness is in the process. Or the way we interpreted before, this is Shannon's first theorem, the difference between these two is the compressibility, or call it redundancy. That using the original symbols is not necessary. There would be a way to compress And the goal is again given by the Shannon entropy rate. Here we've extended this now to the infinite L notion. So you have this sort of redundancy in how we're using things versus what's actually a property of the process. And there's a way to think about this. Again, if I'm, if I bought one bit of storage, I have to put it somewhere. Now, of that information, one bit I just stored, there's some piece of that that is the intrinsic randomness of the process, and then what's left over is, well, in this case, kind of wasted storage, or redundancy, or to the extent there is redundancy, then you should be able to extract that by a clever encoding, and therefore encode the process into something that looks more and more like a fair coin. So we can use this notion of redundancy to motivate one way of monitoring how the entropy convergence process comes to its asymptote. So what we're going to do is look at a kind of a long word version of the redundancy where we compare the words of length L, the distribution, to a uniform distribution over the words. Or we can shift that around and actually adapt this to a notion of redundancy that's appropriate to the block entropy curve. So in here we're using words of length L and also their probabilities to build our code. And then the process has this asymptotic per symbol randomness. You could kind of imagine that this is sort of a bias coin with that entropy rate. And to the extent that there's some difference between these, then there's some redundancy in using just the words. So if we now plot the kind of a generic block entropy curve and then compare that to this, what would be an IID approximate, imagine an IID process that has the same entropy rate, but now that's a memoryless process, so that goes back through 0. Has the same slope as this does up here. And then there's this distance between the two. We're using more information in H of L than, at least if we looked at very long words, would be necessary. So there's this distance here, and that's a measure of redundancy. We're sort of comparing our source to a bias coin example that just has the degree of randomness. Or we can, since we're now taking derivatives of everything, DDL derivatives, we can think of redundancy per symbol, just basically divide everything by L, or look at this big R of L, and look at its slope. Well, a little bit of algebra shows that that's just H mu of L minus H mu. So we end up with this entropy convergence curve, and then the redundancy per symbol is just the distance between our overestimate of how random the process is at length L versus the true value. Okay. Now we do it again. I'm going to look at the rate of convergence of the entropy convergence. So I can look at, it's like the 2-point slope again of that previous entropy convergence curve, and I'll call that del squared. So again, you're thinking of del here as d, the big L, discrete derivative. And this is kind of the generic case here. This actually, it's not monotone anything. It can kind of vary around other than the fact that it's negative. And this being negative, actually, it's a good exercise. This predictability gain being negative means that H of L is concave down. Monotone increasing and concave down. It also, the negative thing means that H mu of L converges from above and so on. But now we're looking at that. So this is another thing. To the extent it hasn't reached 0, we're not at the asymptotic word length. We can argue about boundary conditions. The one we take here is that at H of 1, the intercept is the single symbol entropy minus the log of the alphabet size. You kind of work that through to make sense. Now, language gets a little bit confusing here. So what is the predictability gain? One way to say it is it's the rate at which unpredictability is lost. Well, maybe it's just better to stay with predictability gain. Right? I go from this length of word, look at a longer word, the entropy, my entropy rate estimate has dropped, therefore I'm predicting better. That's why it's called a predictability gain. But entropy is a measure of unpredictability. So if you really want to phrase, some simple phrase, it's unpredictability loss. I just mentioned, right. So being negative means that the H of L is concave down. And perhaps more suggestive in terms of getting some intuition about this, what happens is when at a particular L you get a large value of the predictability gain, it means that symbol you just looked at, maybe going from words of length 4 to length 5, suddenly you get a big predictability contribution, large in magnitude, it's negative. That means that there was a large drop in your unpredictability, or at least going to that word length. The system is much more predictable. So here's an example of the golden mean process. So we're calculating out this predictability gain. This was done basically just by writing down a model and generating lots of strings and estimating the word distribution and then p log ping that, and then taking derivatives of the block entropy curve. So here it is, predictability gain as a function of L. And what you see here is, well, words of length 1, again, that you're just approximating the golden mean process as if it was some kind of biased coin. You're just looking at words of length 1, which are zeros and ones. Notice how the predictability gain gets very large negative. There's a large drop in h mu of L when I look at words of length 2. Why? Well, we happen to know, since we designed it, that the second measurement should be particularly informative because we can learn that there's one word that never occurs, 0, 0. So going from words of length 1 to words of length 2, there was a huge gain in predictability because we could see the restriction. It's much more predictable. In fact, that's all we really need to know about the golden mean process, statistically speaking. And that's shown because we look at words of length 3, length 4, it reaches 0. There's no other predictability gain looking at words of length 5 or 6. Well, at this point, you could extrapolate that I'm going to take a derivative again. We're going to stop just because the language gets too complicated. And there's no particular reason to stop. In fact, this process of taking derivatives can keep going on and on and on. So there's actually a whole hierarchy of different kinds of block entropy, entropy convergence, predictability gain, and language fails me for the higher level derivatives, but that doesn't mean that there couldn't be processes for which the higher order derivatives of the block entropy are important and informative somehow. I can't think of how. I have examples which we'll deal with, but so what we did is we took derivatives. We started sort of at level 0, block entropy. We looked at the entropy rate approximates. That was the first derivative of H of L. And then we looked at the predictability gain, which is the rate of change of the entropy rate or the curvature of the block entropy curve. Well, that's as far as we're going to go up this hierarchy. Now what we're going to do is come back down by taking integrals. Right? We now have these curves, predictability gain, and we're interested in the areas which give us some sense of how long it takes for the curves to reach their asymptotic value. So we can go up the hierarchy by taking these derivatives. Arbitrarily, we're stopping at del squared, and now I'm going to take the predictability gain and start integrating it, right? So the basic strategy here, which I'll apply today twice and then Thursday one more time, is if this is the predictability gain curve, if you wanted to some crude measure of how long it takes to get to the asymptotic L, where in this case its asymptotic value is 0, I can look at the area. Large area takes a long time, small area converges quickly, just a crude measure. Okay, so what we're going to do here is just take these and just sum it up. We have the asymptotic value, which is 0, and we look at the curve and we just sum these things up. So just sum up the del squareds, the information gains at each L. We call that the total predictability. Well, why do we call it that? Well, it turns out, and maybe I should at some point spend some time proving these things, the proof of this is actually in that paper, our regularities unseen randomness observed paper, RURO. You can show that this G quantity, total predictability, actually is this redundancy. It's the difference between log of the alphabet size, remember just the raw messages, if you will, minus the true randomness of the source. It's the redundancy in the source. In some sense, it's the amount of information you have to extract to see the true randomness, which is another way of phrasing what we meant by convergence, getting to the asymptotic value. So this is the amount of information you extract to account for all the correlations. Once you get all the correlations, you're conditioning on a long enough history, then you can see the true randomness of the source. Fall short of this, fall short of extracting this many bits, the process appears more random than it really is. There's excess randomness, apparent randomness. Okay, so that's one integral, right? I took a derivative to get the curve, and now I'm integrating the area between the curve and its asymptotic value to get some information measure. So first thing, total predictability, and it turns out this is very simple. It's really just related to how redundant the original source alphabet is compared to the true randomness. Yeah?
I have a question,
Please.
which is, so we just took derivatives, and now we're taking integrals, and is there any reason I should just think of that as you going back up the derivative scale that you just took, adding a constant maybe?
Yes. So, right. So the punchline here, let me just give it now, is that the constants of integration are new measures.
Oh,
Yes. So the first one here is the total predictability. It's this redundancy. A good thing to know about a source. I mean, it's good to know what the entropy rate is. Well, and it's pretty easy to turn that into, again, think of that anatomy of a measurement plot. The difference with the alphabet size, as if you were democratically using all of the symbols, uniform distribution. Right. So this one's easy to interpret. So what we're doing is I'm sort of just turning a crank here. We took derivatives, and now we're integrating. We're going back down the hierarchy, and at each stage we're going to be confronted with a constant of integration. And the question is, what does it mean? Okay, so now probably the most important thing, certainly for today, is let's go back down, and I'm going to apply the same recipe to looking at the entropy convergence, right? H mu of L convergence, and how it comes down to H mu. So the same recipe is I'm going to sum up the components, at each L, sum up the apparent randomness, this overestimate, H mu of L, and compared to H mu, the true randomness. That's the excess randomness. In fact, I'll call it the excess entropy. And of course, if this area is big, it means it takes a long time, large L, to converge. If it was short, it would indicate roughly quick convergence, small L's. So it's kind of like a length, convergence length. And it's, that said, the definition is quite simple. I just simply sum up from words of length 1 out to infinity the difference between H mu of L and H mu. Now think of the sum here as the integral, just like we were summing up before. And kind of the analog of dx here is delta L. Well, that's just one symbol, so I'm not putting it in here. So these are, think about this, we have entropy rates, bits per symbol, but now I have in this fake integral, I have integral dx, but the dx is one symbol. So I have bits per symbol times a symbol. E has units of bits. So that's what this area has, units of bits. Right, and I integrate a rate against a length, and I get just units of bits. We can also think of this as a redundancy. I'm just rewriting it here, right? This is the per symbol redundancy I defined a couple slides ago, which was just, again, this difference. This is just a reinterpretation. If I'm using words of length L and their probabilities to build a code and not aware of what the entropy rate is, I have a code system that is redundant by this many bits. And I'm just going to integrate up this redundancy. Okay, so what are the properties of this excess entropy? Well, again, units are bits here. It's always non-negative. Again, just because it's this area, it controls convergence to actually being able to see H mu, the true randomness. And the slow convergence, large area, means correlations exist at long words. And again, this is complementary to the entropy rate. I mean, you can imagine here, just graphically, I can draw any number of convergence curves like this and shift H mu around. So there'll be processes with various entropy rates and different excess entropies. There's no necessary connection between these things. Fix an entropy rate, think of all the processes that have that entropy rate, there'll be a whole range that have different excess entropies. Okay, now what I want to do is, so this is the entropy hierarchy way of backing into this concept of excess entropy. But there are other interpretations that become sort of more and more suggestive and help sort of make the point that we actually have a new measure of memory in a process in this. So one is just a kind of a graphical interpretation. So before, remember, we thought that we first started out, we had h of L, and that was growing something like h mu of L, slope times length. There's another way to think about the excess entropy, and you can show, and that's what that paper shows, is that the previous definition of it is the asymptotic difference between the block entropy and this memoryless source, this biased coin with the same entropy, right? So that was, I showed you before, that was h of L minus this linear curve that went through the origin, this difference. With this scaling form, I mean, if you write down a limit like this, basically what you mean is that you have a kind of an assumption for how the block entropy is growing. That it grows linearly, but now there's this offset. So the graphical interpretation is here's h of L, growing, 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 finally gets out here to large enough L, and then each new symbol is adding h mu bits each time. But there's this linear asymptote it's going towards that has a y-intercept. That's the intercept is the excess entropy. I mean, if you wanted to be really sloppy about it, you'd say, well, it's sort of like at time zero, or it's what the process is storing itself. I have to go correct that phrase, but you know, I mean, what does it mean to have a L equals 0 intercept? But basically, it's this scaling form. Like this is a better way to think about how block entropies grow. If I was thinking just that, in a sense, what I'm doing is approximating h of L out here with a line that goes through 0, a memoryless IID source, a biased coin. And if I draw a line from here up to that h of L, notice it has steeper slope. As an approximation, just thinking it scales this way means your approximation scheme will always overestimate the entropy rate. Now, if you let this linear curve free up, and you also estimate the y-intercept, then you get a much better estimate of the entropy rate, and more quickly with less data. But anyway, so that's the other picture, kind of the geometric picture of what the excess entropy is, as opposed to total redundancy. Another nice one is the cost of amnesia, that if you were out here looking at words of length L and making some sort of approximation and getting a pretty good estimate of the slope up here, and then someone hit you on the head and sort of lost memory, and you're only approximating it with this memoryless IID source, h mu L, there's this amount of bits you'd have to regain to start predicting the source at the entropy rate. So it just, you forget what you know, and you have to regain that information from the source to predict it at the entropy rate. And there are probably other interpretations. Maybe it depends on the context and problem you're working on. Now, probably the most important interpretation of this is the following. And maybe it's worth for you to read through the paper and the proof that connects the previous two definitions with this one. So the excess entropy you can show is the mutual information between the past and the future. So this is where we come almost full circle back to thinking about dynamical systems or stochastic processes as communication channels. That there's been some history, here you are in the present moment, somehow some memory is remembered from the past, and then that's used to produce future behavior. So I can think of the present moment as if it's a communication channel that communicates the past to the future. And I want to know what's in the box, what's in the channel. Well, so a first crude measure, this looks very much like the channel capacity, the mutual information between the past and the future. That's the excess entropy. Now, it's not really a channel capacity. If you remember Shannon's definition, it was kind of an engineering approach. I have this box I'm building, and I want to know the best it can do, so I maximize over all input distributions. Here we have a process given to us, and so we know what the input distribution is. So it's not quite a channel capacity in an engineering sense, but you could call it a channel utilization. The dynamical system, or any physical system, it's communicating its past to its future, and it's generated its behavior, therefore it's generated its past. That's the input distribution, and that's going to exercise a certain amount of whatever the mechanism is in the present moment that is storing the information. So again, this is probably the most pregnant interpretation of the excess entropy, this past, future mutual information. And it really says, we are thinking about systems as channels. Now, one quick note here that will come back to us in the spring. If you remember, the mutual information of two variables x and y is the same thing as the mutual information between y and x. So it's symmetric, right? If you remember the p log p form of it, the argument of the logs is the joint distribution over the marginals, and that's symmetric. So this is, E is a quantity that doesn't distinguish past from future. It's just, the process stores as much information from the past and communicates it to the future as it stores information from the future such that it produces the past. E is not telling us that there's any kind of, can't tell us there's any sort of temporal asymmetry, which maybe that's fine. Turns out to be wrong, but just to note this particular property in there. Okay, so how about some examples of E? Fair coin, okay. Again, and there'll be different ways. Most of these simple examples, we'll be able to read it off graphically. Okay, so here, plots I showed you before, fair coin, bias coin. What's the linear asymptotes offset? 0. 0 excess entropy, 0 bits of apparent stored information, or at least 0 information shared between the past and the future, which makes sense because by definition, the fair coin, the current flip doesn't depend on what happened in the past. So that's good, right? So nice 0 bits here. And then again, just like now at this point, it's kind of a whipping boy. The IID processes, no memory. So this is now going to be my proxy for why they're uninteresting. E equals 0. We've talked about the period 2 process before. So 0, 1, 0, 1, 0, 1. And we showed the block entropy curve. It's easy to calculate. It just goes up at length 1. At length 1, it's just 1 bit, right? If I'm looking at this with a window of length 1, the statistics are 50-50 for zeros and ones. It looks like a fair coin with L equal 1. So that's an example of overestimating the entropy rate at L equal 1. Then, of course, I go to L equal 2, and suddenly I see that they're now 2 forbidden words. 0, 0, and 1, 1 are forbidden. So, but now there are 2 events, 2 words that occur, 0, 1, and 1, 0. But that's still 2 events equally likely, so the block entropy stays at 1. But now we're taking derivatives, so I can take derivatives of this. And so I have the H mu of L, that my entropy rate estimate is 1, and then at the next length 2, that drops to 0. The process becomes exactly predictable using length 2 words or longer. So we have 0 bits per symbol, it's predictable. We look at the y-intercept, that's 1 bit. So we have excess entropy of 1 bit, or you could think, okay, what's the area in here? Well, it's just 1 symbol by 1 bit. But what is this 1 bit here? It's simple, it's just the phase information of the process. Did I just see a 0 or did I just see a 1? And somehow the process is remembering that. Here's a more interesting example, that period 16 process I showed you before. So here's actually that length 16 template word I was using. And again, this goes up at length 12, it finally levels off. So we have 0 slope out here for L greater than 12. So that means entropy rate is 0. Now what's the intercept? We just pull that back and we see that it's 4 bits. 4 bits of what? Well, it's period 16. So the 4 bits is sort of the answer to the question, what phase are you in? And you have one of 16 answers. So log base 2 of 16 is 4 bits. And here's, maybe kind of interestingly, here's the entropy convergence curve. So showing the sort of monotone decreasing property. There's some, as I'm going out longer and longer words, my ability to predict is improving. the apparent entropy rate's dropping, although there'll be some range of word lengths where that's just not additionally informative to me, but sometimes it'll drop. So then you'd also expect the predictability gain to be large during these drops. And then here it's finally at length 13, you can see that the entropy rate's 0.
So from interpreting this, rather than saying that after 12 measurements, then we can predict what the next 4 would be?
Yeah.
But is that just
And-
an artifact of this specific sequence?
It
Like,
absolutely is.
1, 1, 0,
Yes.
3, 3, 5?
Right. Yeah. This was chosen to do this. So actually, there's an interesting,
We shouldn't expect that for a period of 16.
no, notice how I've been careful to say, the general properties I'm only willing to commit when L is greater than the period P. But it turns out that there can be certain kind of statistical properties of these chosen templates that give different convergence properties, right? So this one will be different than, another period 16 sequence is 15 zeros and a 1. So think about that. If you get lucky and you drop in and you measure a 1, you immediately know with one measurement what the phase is. But if you see a 0, it's particularly, you've got 15 choices left. So there's some interesting balance between the specificity, the information, then how vague the symbols are coming back for you to, quote, synchronize and actually see the period. So you'll have different shapes here. So we'll go over that on Thursday. Yeah, in the periodic case is kind of nice. They let you see really clearly without worrying about extra randomness being thrown in. So now, so one point about this, we're looking for important properties of processes, stochastic processes. Notice how the entropy rate doesn't distinguish any periodic process from any other. It's 0. So the excess entropy now at least is giving us the handle on the periodicity. That's kind of nice. Maybe it doesn't capture the shape of the convergence and the synchronization question, but we'll get to that on Thursday. But at least it's, for periodic process, very clearly a measure of phase information. Entropy rate's useless. Doesn't help us. All periodic processes have 0 entropy rate. Predictable. Okay. Again, our workhorse processes here. We will look at these things from 12 different ways. The golden mean process, well, I showed you the block entropy curve before, and now what I've done is put in the linear asymptote, which you can finally see here is this dashed line. So, like I probably should rescale this, right? So it converges basically at L equal 1, but I pull back. There's a little bit of excess entropy here. Interesting question. How do I calculate this excess entropy? With all the other examples, I was able to argue. The line goes through 0. It's the log of the period. Excess entropy, turns out, is past future information is quite hard to calculate for general processes. We'll give you a closed form solution to this in the spring, but here, just numerically estimated. Generate lots of words, estimate the word distribution, calculate p log p over the word distributions, plot it, fit a linear function, then extrapolate back to 0. And that's, at least now, the only tools we have. Even if I gave you the two-state Markov chain version of that, how you get the excess entropy is kind of tricky. So we need to actually talk about some other things. And this picture here, the golden mean process and this picture here is sort of indicative of any sort of R block process. In particular, well, for kind of spin block processes, which maybe we'll have a chance to talk about that. But and generally, it looks like they're a closed form that you can write down in this one very restricted case. And so you can calculate this for the golden mean. So the entropy convergence curve, if I haven't looked at anything, looks like a fair coin, and then it drops finally at L equal 2, and then we reach the entropy rate. Again, this is telling us if we had the model, the order 1 Markov chain, we could calculate the entropy rate exactly. But a similar closed form expression for E, other than very special cases, is hard to come by. Okay, random XOR. And I give you this example because it's typical. What does that mean? Just pulling random processes, examples out of the space of processes, what happens? So the random XOR is typical. So here's the definition, finally. Flip 2 coins, XOR them, that's the next symbol. And this is done in blocks of 3. Okay, once you generate, you go back and look at the word distribution. And here's the block entropy curve. It's maybe a little easier to see what's going on in terms of the previous question of what the asymptote was. You couldn't, until you put in the dashed line, it's hard to see. So that's what the linear asymptote is. Looks like about 2 bits. Turns out it's not quite that. But the thing I want you to focus on here is the h mu of L entropy convergence plot. In fact, it's like you were saying before, it's just this slow, well, actually, it's slow. It depends on what you mean. It's actually an exponential convergence, but it never gets there compared to golden mean, which got it right at a finite L value. So there might be some, interesting structure down here, but eventually the typical sort of finite memory process, and I have to define really what I mean by memory, but finite memory process has this exponential decay, like that for large L. So that means you can make good approximations, just go out to some L, but you're not going to get... Now, what's curious about this is that this process, it has a simple definition, has what looks to be kind of statistics that only converge in the infinite L limit. You might think, oh, gosh, that's an infinite memory process. It turns out it isn't. We'll see that this thing actually only has 5 internal states. So even very finite memory processes can have this kind of exponential convergence, which might make you think that it had infinite memory. Because what this means is that there are correlations at arbitrarily long words. So there's a puzzle. How can a finite memory process generate infinite range correlations? Like, the practical response is, I don't care, it's exponential convergence, I'll just chop it off. Well, that's not a principled answer, it's a practical answer. So in general, we call processes that have finite memory, we call them finitary. And I'll give a better definition later, but basically it means finite excess entropy. And then in that case, you can show that this entropy convergence curve decays just under that one assumption exponentially fast with some exponent. And yeah, but you can actually write down a sort of finite formula for it in terms of this exponent. If you estimate the decay rate from that, then you can get an expression for E. For random XOR, it's about 0.3. Which means, in particular, this was a really bad graphical fit. Really bad. So, okay, so the sort of final example will be what Quinn mentioned. But we've seen this already, it turns out. An example, what you might call an infinitary process, infinite excess entropy. And these are the fun ones. So here's a plot, block entropy and entropy convergence for what's called the Morse-Toohey process. It's actually kind of invented by Morse and Toohey back in the 20s and 30s. But it turns out it's the same language as the symbolic dynamics of the logistic map at the onset of chaos, right? At the end of period doubling, just before chaos, right at the onset. If you look at the binary generating partition, and then that's a process, turns out it has infinite excess entropy, infinite range correlation. It's a highly structured process. And it has this H of L that's essentially logarithmic, and it just never really reaches a linear asymptote. But very, very slowly, right? It's like a worst case. It always seems like it's... so one thing I want to point out here is in the plots. Before, I was showing you these plots with word lengths of 1 to 5 to 10. Here, actually, this is times 1,000. 1,000, 2,000, up to 5,000 length words. It's like, wait a second. How could you do that empirically? Well, at the onset of chaos, right, the Lyapunov exponents are 0, and it turns out the entropy rate's 0. So this is sort of, what's it mean, asymptotically predictable? You stop short, there'll be a little bit of approximation, at least to apparent randomness. So it's, asymptotically, the number of words that you see is sub-exponential. Therefore, when you look at take the limit, however you define h mu, it goes to 0. And that means there are very, very few words. So you can actually go out and empirically estimate for zero entropy but high complexity processes, high memory processes, the word distribution out to very long words and get good approximations of these things. Here it's kind of blown, this section is blown up from words of entropy convergence for words from 0 to 30. Again, it's kind of stepping down the whole long ranges of words, that word lengths that don't improve your predictability. It's quite structured, actually. These steps get longer and longer and longer. We can come back and talk about how to analyze that. There's a technique called renormalization group that lets you calculate all these properties exactly. Comes out of statistical physics, phase transitions. So in fact, this is kind of a signature of systems at phase transitions that have long-range correlation, so-called critical phenomena. They have infinite memory. Physicists say, oh, infinite correlation length. We now say infinite excess entropy. In fact, this process is extremely structured, and you can write down, if we have time, we'll do this, what's called a context-free grammar that actually uses not a finite state device, but a device with a stack or so-called push-down automaton to generate it, which is sort of a puzzle, right? Because we just write down, x of n plus 1 is r times x times 1 minus x. That's just this little quadratic function over the real interval that somehow, with that one parameter setting, you set r to the onset of chaos, 3.569, whatever, somehow it's got embedded in it some mechanism that has infinite range correlations. It's doing some kind of calculation that, in this particular case, we can map back over to formal language theory and show it has one of these context-free grammars built into it. It's very, very odd. It's also what initially interested Morse and Tui, but that was long before computer science was a discipline. So some interesting early history here of the symbolic dynamical systems studied. Okay, well that's actually it for today. Again, we're sort of maybe a lot of concepts, but the key one is this excess entropy. So first we were sort of focused on how random is a process, and then we realized that's sort of problematic. When you have structured processes, then you have to worry about what word length you need to go to see that it is actually random at some level. And then you start looking at how the convergence process of getting there, and then what you end up with are these total predictability and now this excess entropy. And they have these nice interpretations of redundancy, total redundancy, how much information you need to extract to see the intrinsic randomness, h mu, or dispatch future mutual information, like the excess entropy. So taking these derivatives going up and then taking integrals coming back down is actually, it's a nice crank to turn. Suddenly we have these new information measures. And oddly enough, these are only about 10 years old, the actual use of them in dynamical systems. So we stopped a little early. I'm certainly willing to take some questions.
Okay, yeah, I got one.
Great.
So back 2 slides. Looking at the RRXO.
Yeah. Uh-huh.
You said that the estimation of the slope of E was a very bad estimation. Why is it you say that?
Oh, sorry. Yeah, right. Here, the way I drew it, the linear asymptote would be 2 bits. It's actually 2 1/4 bits. So this is although we're going out the length 18 words, which is a little bit trite because this has high entropy. It's when you try to slap on this linear asymptote, it just the offset is really sensitive to how you lay it down up here. So we're off by 10% at least, even though in some sense we put a lot of effort into generating a good sample of the 250,000 words at length 18. Yeah, so that's why it's a bad estimate. Yeah, but we'll come back to ways of calculating this basically to arbitrary precision. But it takes some more technology to get there. We need to get to this concept of state. What really are the effective states in this process? I mean, there's this sort of dichotomy between this is a process that's easy to define. You can imagine generating all sorts of examples like this, and it's just interesting that they can generate this kind of exponential decay, statistics, correlations over words much, much longer than the kind of length 3 template that the rules operate on. Strange. The golden mean is sort of, in a sense, the atypical. It really is just no consecutive zeros. That's a finite word and it has calculate things finitely with a Markov chain, order 1 Markov chain. Here, what's the order of the Markov chain? Actually, it's infinite. But it's finitely defined. So what's going on here? All this notion, especially if you've been, if you studied your physics well, your statistical mechanics well, this is really a puzzle. So, yeah.
I'm curious, if we go back to the idea of the mutual information between past and future, is there a notion of sort of an equilibrium state that you can get into when the, I'm not sure how to define it, but is there some relation between the past and the future reaching a certain level where?
Right. So the question is about equilibrium, and the different ways to respond depending upon what one means by equilibrium. So one notion of equilibrium here is that you're sort of seeing the asymptotic statistics, and until you have the right window length, you're sort of out of equilibrium. You're overestimating the entropy rate, so there's some sort of finite approximation you're making, and it's still in tension with the actual statistics of the process. In other words, you're not seeing it over this length that you can detect the randomness at the level of h mu. So yeah, you can imagine, for example, past future mutual information. One way to approximate it is you just look at pasts of length L and futures of length K and let those two things grow. That's one way to get to it. Turns out it's really hard to estimate. And this is just the first hint that it's a little bit subtle. This is a different technique, linear fitting the linear asymptote to it. Fortunately, there's nice, well-behaved, extremely convergent and accurate methods for estimating. That particular problem puzzled me for over 15 years. It wasn't until about 4 years ago we solved it. So, yeah, we'll have a lot to say about that. But now for you, it'll be straightforward. For me, 15 years. Yeah.
So you might have mentioned it. It seems like one intuitive way of thinking about this would be that the most information you could possibly have to make the best prediction would just be like what phase you're on again, like in the period one. It's like whether we're on the first random, the second random, or the
Right.
one, right?
Right.
But that would be less than 2 minutes.
Yeah.
Right?
Yeah. 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 There are a number of different. Yeah. For a while, I convinced myself it had to be 2 bits
Yeah. Or
because.
like 2 to 3 or something.
Yeah.
Phase.
Yeah. So I now know better. So, yeah, Alec.
There are cases when there were long strings where you won't be able to tell what phase you're in, aren't there? Like where you won't be able to stick to your phase.
Right.
And possibly that's why it never converges.
Right. Right.
Because you could have an infinite length word where you would never say, oh, here we can tell that this 3-length word violates the rule, so therefore, this is the appropriate phase to be in.
Right. Right.
But even with that, I mean, that would just be saying it would take infinitely long to reach that asymptotic difference. But the difference we're approaching here is larger than that. It's not.
My point is that it would take infinite length words to fully sync.
Yeah, so let's be clear. What could sync mean? Well, one is we have this kind of framing where we're laying down, 2 fair coins and the next. So this is kind of this framing of length 3. Now imagine you generate a process and I just give it to you. I don't tell you how it started or anything. I'm not telling you what the framing is. How do you discover that framing? I will show you what the effective states are for this in the spring quarter. It has, just to give some meat to the bones here, it has 35 states. Most of those are what we call recurrent states, which actually are the correct answer to this, how do we come to know the framing? And then there are so-called 5 recurrent causal states that kind of generate the statistical equilibrium core of the process. But it takes really long time, many words kind of trickling down through these states to figure out how you get to the internal 5 states. That won't make much sense until we get to these causal states and so on. But that to me says the fact that there are 31 of these transient states means that there's no simple verbal description of that convergence process, the synchronization problem. Happy to be disabused of that view if someone had a nice simple explanation, but yeah. Great.
Well, I don't know how useful it is to say this, but I guess I kind of have a comment about things that have infinite unpredictability. As we need an infinite string, like especially if it's based in real numbers, it seems like that would be something that you'd expect, since a real number is basically an infinite state, or it has an infinite number of states, one for each bit, in the decimal representation, let's say.
Right.
So I would think that it would be pretty rare that you could, explain functions on the real numbers with a finite state machine, I guess, or be able to know with a finite sequence of those.
Right. So there are sort of parallel constructions. So what we're doing here, and I've already kind of stepped into it without giving you much background, this connection in the Morse-Dewey case, onset of chaos case, to these other descriptive frameworks for processes, namely out of the theory of computation. And these are the most immediate analog of our finite Markov chains of finite hidden Markov models are the automata. And then in that arena, there's this Chomsky hierarchy of more sophisticated mechanisms, all based on discrete time, discrete alphabet processes, if you will. They don't quite frame it that way. They call them formal languages. There have been, in the last 20 years, constructions of the same type of computation theory, but over real numbers and similar kinds of hierarchies. And there's a close connection to dynamical systems there. So we might have some time to talk about that. We're mostly going to focus on discrete symbol, discrete time processes. We'll be able to make some direct connections to more traditional computer science models. Yeah, generally, adapting these ideas to continuous state process is really interesting, and that is the research frontier. There's special cases we can do, but it's nowhere near the level of completeness and kind of accuracy of estimation and even practical application that what we're going to cover. But it's clearly important. So next week, at the end of next week, which will be the next week of the last lectures for the winter quarter, I'll give a kind of, I guess, a week from Thursday, I'll sort of paint the broader picture where we're going in terms of some of these issues. Here we're just the introductory stuff, kind of ramping up to seeing what, in this case, that information isn't this unitary thing. There are different kinds of information. We now have total predictability, excess entropy, entropy rate, lock entropy. Okay. See.